All right, great. Well, welcome everyone. It's great to see a good turnout on a Monday afternoon. I'm excited to welcome today Professor Rob Howe. So Rob is specifically the Abbott and James Lawrence Professor of Engineering at Harvard in the Paulson School of Engineering and Applied Science. And he works on a wide range of really exciting things related to really understanding motor control for both robots and humans, and also in the space of surgical robotics. And so today he's going to talk to us specifically about laminar jamming and its applications to a number of different, I understand, robotic and other systems. So with that, looks like your slides are up. And take it away, Rob. Thanks so much.
Okay, thank you, Laura. I am pleased and honored to be able to speak here. The Bay Area is one of my favorite places in the world. And while I am sorry I cannot visit you in person, especially because I think the high temperature today in Boston was 24 degrees, I am always pleased to think about Berkeley and the Bay Area. So thanks again for the invitation. So today I'm going to talk about a new technology which we think could be something of a bridge. I'll get my slides to work here. So at this point, we've sort of explored two different paradigms in robotics. There's traditional rigid robots. They have rigid links, well-defined joints. And then more recently, just in the last 10 years, we have soft robots, very flexible, often infinite degrees of freedom, continuum deflections, and often powered with fluid. So they're very different in their behavior. And this results in very different applications. So traditional robots, of course, can move fast, they can apply high forces, and they can be very precise. Whereas soft robots are adaptable, they can be quite robust, and they also work quite well with the human body. It's simple to interface them. So we're asking the question, is there some way to allow controlled transition, to allow the same robot to exhibit both of those behaviors? And of course, the answer I'm going to try to advance is yes. In fact, you can. And the way we do that is with layer jamming. So I'm going to start with an explanation of the basic phenomenon. So you start with some layers of a compliant material, and a particularly effective material is regular printer paper, the same stuff you put in your inkjet printer at home. Then you put it in a plastic bag, some type of an airtight envelope, and hook it up to a vacuum source. This means the atmospheric pressure pushes those sheets together and they become locked by friction because of that increased normal force. And the behavior becomes radically different. So on the left is the unjammed state. So that's 20 pieces of printer paper in a plastic bag, quite floppy. However, when you hook it up to a vacuum pump, it becomes shockingly rigid. And usually at this point, I would have a demonstration. So you'll just have to take my word for it, since we can't pass anything around today. But you can see here, it'll withstand quite high loads. That's a 1 kilogram load on 20 sheets of printer paper on the right. And the increase in stiffness is quite remarkable. It goes as the number of layers squared. So our 20 sheets of printer paper become 400 times stiffer after you apply the vacuum. So the result is a very thin, lightweight, low-cost structure. It can be very quickly activated, and it's completely reversible as well. And just to get into a little bit of the fundamental behavior at this point, so we start out with the vacuum off, and now we apply a force in what we call a 3-point bending configuration. We have 2 pins holding this up, apply a force in the middle. We get a downward deflection, and if we plot the force versus deflection, for at least a good bit of deflection, it's linear and represents a low stiffness. But when we apply the vacuum, now the layers are cohesive. They no longer slide with respect to each other. And so now we have a much higher stiffness. And by the way, can you see my pointer here? Is my mouse visible?
Yes.
Great. Okay. Now, if we keep pushing, though, keep pushing downward on our structure, we start to get slip. So we've now generated a shear friction, a shear force that is higher than the friction. So now we get sliding, and now the stiffness becomes much lower. The offset is the frictional force, but the stiffness from here on out is the same as just bending the sheets independently. Now, this, of course, means we're pushing against friction, so we're dissipating energy, and we've created a friction dissipation loop, or a friction damper. So again, this damping is something we can use in designing mechanisms. So today I'm going to talk about some of the static behaviors, then mechanical modeling that describes what goes on, and then the dynamic behavior, in particular, how we can use this damping behavior for impact control. Then we'll go through some fun applications, and finally talk a little about our most recent work on design space of jamming. So the first cute trick here is shape locking. And you can see we can assume a shape, pull the vacuum, and our jammer will hold that shape. In a more manipulation-related application, we can create a structure that looks like this. This is a NewNet soft robot actuator, a finger, if you will. When you inflate it, it bends. And to the front surface of it, we've adhered a jamming structure. So again, this is, I believe this one's about 15 layers of paper inside a plastic bag. We turn the actuator on, it bends. Now, if we release the pressure, of course, it just goes back to what we had before. But while it's in this bent shape, if we turn on the vacuum, now when we turn off the pneumatic actuation, we retain the same shape we started with. So this is a kind of a clutch or a brake for a soft robot, and allows you to remove the actuation, but retain the shape you achieved. And you can do some fun things with this. So here, for instance, we show that we can adapt to shapes. And if we push it beyond the yield point, it now retains that shape going forward. And we can also use the same approach to create and destroy joints in a robot manipulator. So on the left here, this blue shape is a piece of stiff rubber, and we have a hole through the middle of it that's slightly off center. So now if you pull on this actuation cable, this thing will curl up. However, we've attached 3 of these jamming structures with a slight gap between them to one side. Now, if we pull on the cable without turning on the vacuum, we just get constant curvature, the kind of shape you would expect if the jamming structures weren't there at all. But if we apply the vacuum before we pull on the actuation, now you've got these gaps between the jammers, which are much softer. So the deformation is concentrated at those pseudo joints. So we have the ability to turn these joints on and off then. And this has an immediate application in robot hands. So if we don't turn on the jammers, the fingers are very adaptable. Now, when we pull on the cable, they'll simply adapt to the shape of this large ball we've put in between. However, if we go to pick up a small object like this 2.5 centimeter ball, this approach won't work at all. Instead, we now apply the vacuum before we pull the cable. So now we have a jointed structure. We have these points where the deformation occurs. Overall, the fingers are much stiffer. So now we can get a stable grasp of a much smaller object. So here we have about an 8-to-1 difference in size, which wouldn't be possible with either one of these approaches alone. It's only through the combination with jamming that we can enable that. And we were amused to discover that, in fact, this had been previously, this sort of approach had previously been discovered by the octopus. So these biologists observed a lot of octopus behavior, and they discovered that even though their tentacles have an infinite number of degrees of freedom, they like to use joints. They like to have certain regions of the tentacles where most of the bending occurs. And their conjecture, of course, is that this simplifies control. It's hard to think about how to move an infinite degree of freedom system, but if you have a few joints, the control becomes much more straightforward. Okay, now let me dive into the mechanical modeling. And our goal here is to understand how this combination of material selection, the geometry, and the loading can work together to provide a desired structure to perform some function. So of course, slip is the main action here. So we have, with the vacuum off, we push on this low load, we get a very low stiffness. We apply the vacuum now, and we have this cohesive behavior with no slip. And now we have a very high stiffness until we reach this very high load, where now we do get frictional slip and we have a lot of damping. And to understand this requires some pretty sophisticated modeling. So we collaborated with my colleague Joost Vlasic, who's a solid mechaniker at Harvard. And we went through a lot of very complicated Euler beam formulation. And let me show you some of the interesting results from this. So we started out with a very simple cantilever structure. So we have two jamming elements, two sheets of paper, if you will. We brace them at the end, so they're fixed at this end, and then we apply a distributed load, a pressure all along the top surface, as well as the vacuum. And this is the result. So each of these represents the shape that results as we push on this, where the purple are the parts of the beam that haven't slipped, and the gold is the part that has. So as we increase the load, the slip starts at the fixed end, slowly propagates outward, and then from here on down, everything is slipping as we push harder. And you can then formulate these beam equations in terms of each of the different regions and put them together to calculate the local curvatures and the total deflection. And I'll spare you any further discussion of those, but I will describe how well these models work. So this is, again, force deflection behavior. And the dotted lines are model predictions. This is finite element model predictions, but they're effectively the same. They're very close to the analytical model predictions. And the colored traces you see in each case here are the experimental results. And I don't know on Zoom if you can see, but these colored lines actually have some width. And the width of the lines is the standard deviation of 5 trials for each of these. So you can see this is an extremely reproducible behavior. And furthermore, our models are extremely close. The dotted lines and the colored lines are remarkably close in this case. So at the end of the day, we can use those analytic models to get the functional relationships, the scaling relationships, which are what designers need. So we're able to say, for instance, the pre-slip stiffness is proportional to the number of layers cubed, it's proportional to the pressure you apply, or it's not proportional to the pressure you apply, and it's not proportional to the coefficient of friction. This is the coefficient of friction to the 0 power. However, when you get into the full slip stiffness, it's simply proportional to the number of layers, to the pressure, and to the coefficient of friction squared. So now you can build your jamming structure with desired behavior without a huge cut and try kind of effort. Okay, on to more fun stuff. So I mentioned that you can use these to generate damping, many different levels of damping. And so again, we'd like to have a model that enables accurate design. Here's where things get pretty crazy. So we take our beam equation and we add in a time-dependent term, and you can see we now have second derivatives of both the space and the time dimensions here. So how else can we come up with a model that's easier to work with? And we looked at using lumped element models. So if you're a mechanical engineer who deals with system dynamics, these kind of lumped element models are the obvious thing to use. In fact, I have for years taught a course to sophomore and junior mechanical engineers that covers this kind of lumped element parameter modeling. And the idea is, if I take a stiff spring and I put it in series with a compliant spring in parallel with a friction damper, hang the mass at the end, and I push this through force deflection cycles, they look just like the actual behavior we see in these jamming elements. So that's great, but how do I go from the parameters I use to design a jamming element to the spring constants and damper values that are equivalent? And we worked out a way to do that. You start out and you either perform the 3-point bending experiment, or you can run a finite element simulation, since those are very close to the same. And then from those, you extract the strain energy, how much energy you put into distorting this thing, and the dissipated energy from friction. Now you prescribe energetic equivalences. You say, as I deflect this lumped element model, how much energy am I using up? And then you can work out some remarkably simple relationships that allow you to simply take derivatives of these curves in order to work out what these lumped element values for the stiffness of the two springs and the damping element should be. And then we experimentally validated this with this little apparatus. So again, here's one of our jamming structures, and you'll notice throughout that the material we use for the plastic envelope is this thermoplastic polyurethane, which is slightly green. So that's the giveaway that it's a jamming structure. And we clamp it at one end, and then we can jam it and push it off to the side. And then we have a pneumatic piston, which in the space of a few milliseconds gets this out of the way so we can then measure the response. And here's the result from the experiment. The black curve is the vibration that results when there's no jamming. It's just the sheets of paper flapping around for a little bit. Then we have two different vacuum levels. The blue is a moderate vacuum and the orange is a high vacuum. And you can see those behaviors are very similar between the experimental case and our lumped element model. So we're pretty successful in coming up with a very simple model for this. Now, one of the fun things you can do with this is to control impact response. So we built this apparatus. The blue is a sheet of rubber held at the edges, and we've bonded one of our jamming structures underneath. Then we drop a baseball from a fixed height onto this. So with the vacuum on, this is what the results look like. Ball comes down, deforms the jamming structure, which absorbs most of the energy, and so there's very little recoil from that ball. If we turn the vacuum off, the ball comes down from the same height, and now the jamming structure just deforms and recoils. It has very low stiffness. And so most of the recoil is due to that rubber sheet. And if you wonder how high it went, wait for it, there it is. That's the ball coming back down. So it goes up something like a factor of 8 higher without the jammer activated. And another way to use this would be for landing gear for aerial vehicles. So your standard quadcopter comes with rigid landing gear, really just a little frame that it lands on. And we've modified this by adding some of our jamming structures. So these are our regular old jammers stuck out to the side, so they will contact the ground first upon landing. So let's look at 3 different cases again. One is the no vacuum case. The drone comes in, bam, hits the ground hard. You saw a big recoil there. If we look at the high vacuum case, now we pulled a full vacuum. The drone comes in, and once again, it's too stiff. The landing gear never deform, and so we get a big bounce once again. And then here's the Goldilocks moment when we've tuned the vacuum level just right. So now as landing gear comes in, it absorbs the energy and we stick the landing. And of course, this could be tuned during flight. If you knew the speed you wanted to come in at, you could dial in the vacuum so that you would land smoothly and quickly with minimal accelerations. Okay, now let's look at a few entertaining applications. What do you do with a jamming structure? The first one we look at is building flexures. So here we have 2 of our jamming elements mounted in parallel, and you can see when they're unjammed, it's very low stiffness, a 30-gram weight easily deflects it. But if we pull a vacuum, we can put half a kilogram or even a full kilogram on it, and it holds up just fine. So what do you do with this for a robot? Well, one thing you can do is build a wrist. So this goes between the robot arm and the robot hand. And we have 2 different flexures arranged in orthogonal directions. Now we have this direction that's free to move and this direction that's free to move when it's unjammed, or we can make those very stiff. This means if you come in and perform a task like surface tracking, you can be flexible in the vertical direction so you don't have to control that contact force with the surface very accurately. On the other hand, you can keep the other direction stiff, so now you can get precise control as you slide along that surface. And there are a number of other kinds of applications like this. Those of you who are familiar with some of the first work Mark Rabert did on hybrid position and force control, suggested using a robot to actively control stiffness in different directions. This is a way to passively control and thus come up with higher performance with less work in the active controller in order to get that behavior. Oops, okay, I do have a movie here showing how this works. So this is a piece of foam rubber, and you can see Buza Aktas, my graduate student who did this work. When both joints are locked, we don't get deflection, but we can now have stiff behavior in one axis and compliant behavior in the other. Okay, another application for this is in a wearable orthotic wrist brace. So if you've injured your wrist or you have carpal tunnel repetitive stress injury, you may need to wear a brace. And the brace can restrict motion, which can be great for picking up heavy loads, doing tasks where you have to apply force. It means your wrist isn't subject to the load, the brace is. Unfortunately, they tend to be pretty bulky and heavy, and they limit motion for all the tasks you want to do, whether or not you need that assistance. So our goal here is to use layer jamming in this case to build lightweight orthosis that can resist loads when it's jammed and be flexible when it's unjammed. So the solution to make this work, however, requires some more innovation in the jamming structures. Because if we wanted to make this stiff enough for resisting human wrist forces, we'd have to use a huge thick layer of paper. On the other hand, you could use something like metal, but then its weight goes up quickly. So the solution we came up with is to use sandwich panels. And these are commonly used in structural applications, especially for vehicles where weight matters a lot. So for instance, the Volkswagen Golf has a number of these composite sandwich panels, and the Boeing 787 is mostly composite sandwich panels. And the idea here is you've got your stiff and heavy outer face layers you put on the top and bottom, and then in between you have a core material, frequently a rigid foam. And if loaded and bending, it turns out almost all the stresses are in the face layer, and you don't need a lot of strength in the core. And so you can get performance that's almost equivalent to a solid metal piece or a solid composite piece with only those face elements. So in this case, we've used paper as the core layer and steel as the face layers, and put them together inside an airtight envelope once again. And you can see the behavior is very similar to what we saw with the simple homogeneous bending materials. We have a high stiffness region, we have yield with low stiffness and energy dissipation, and then some elastic return. And in tests, we show that these perform remarkably well in terms of weight performance. So compared to getting the same kinds of stiffness to mass as we would with a homogeneous structure, we do better by a factor of 176. Stiffness range to mass ratio, that is the range of the highest stiffness to the lowest stiffness, jam to unjam, is higher by a factor of 65. And the yield to mass ratio, that is how far we can push this before it starts to slip, was higher by a factor of 15. So in each one of these cases, we get 1 to 2 orders of magnitude improvement in performance. Okay, so back to our wrist brace. How does this work? We have a structure which you can simply Velcro onto the palm of your hand and onto the wrist. And again, we have steel and paper as the sandwich structure. And we measured subjects' range of motion with and without the brace in the unjammed state. And we find that people got about 94% of their original range of motion. So it's very little restriction on natural motion. However, we also examined its benefits in terms of weight bearing. Now, what we really care about is how much effort people have to exert to apply a load. So we restrained their arm and the forearm behind the wrist, and then we applied a weight just around the thenor prominence, around the thumb. and had our jamming structure here. And to measure muscular effort, we used electromyography, little electrodes that measure muscle effort. The results look like this. So in the case where there's no brace in blue, or with the brace unjammed, we saw earlier about the same range of motion, and we have about the same force levels. But once we jam the brace, people can exert a much lower force, 2 to 3 times lower force levels in order to support the same weight. So it's almost transparent when it's not jammed, and greatly reduced muscle activation when it is. Okay, let me then go on in the last piece here and talk about the design space of jamming actuators. So the layers, of course, are what I've been talking about so far today. But there are 2 other media which people have used as jamming actuators. And the first is grains, and this one's been around for many years. And perhaps its most famous example is a jamming gripper. So you take small grains, and actually grains of coffee or kitty litter work particularly well because they have high friction against each other. You put them inside a plastic bag and you pull a vacuum on it. Before you pull the vacuum, they're very free to displace, kind of like a beanbag chair, if you've ever sat in one of those. However, when you pull a vacuum, they become remarkably stiff. And so this is the jamming gripper that actually was commercialized. Empire Robotics sold this for a few years. And you simply have it in the unjammed state, you press it up against an object. When you pull a vacuum, it shrinks slightly and it becomes very stiff, and thus allows you to get a pretty good grip on a wide range of objects. Unfortunately, the company is no longer around. It turns out that this thing works real well almost all the time. But when you're dealing with automation, for instance, an automobile assembly line, almost all the time isn't quite good enough. And if you're only 99.9% reliable, that's just not quite good enough at the end of the day. So it's no longer around, but it's still quite an interesting medium for a number of other applications. For instance, people use this for portable casts for immobilizing limbs in the field, that kind of thing. The third medium is fibers. So these are, for instance, tubes of rubber or rods of rubber, again, put inside a bag and pull a vacuum on them, and they become much stiffer. And this is the least explored of the jamming media. Lots of papers on granular jamming, some on layer jamming, and last count, I think there are about 5 papers on fiber jamming. And one of the interesting applications here is a surgical manipulator. So this can be inserted through a surgical port and then can be bent and locked. So this means it's flexible during insertion, but it can become stiff when you need to apply high forces in order to accomplish tasks inside the patient's body. Okay, so what do you do to understand when you'd like to use which one of these? So we went through a pretty detailed analysis. We considered each dimension, and granular jamming is, of course, homogeneous. Laminar jamming has one preferred direction, the one perpendicular to the sheets. And fiber jamming has one direction that's parallel to the rods and 2 directions that are orthogonal. So dimensionality plays a big role here. And then we went through and we analyzed the kinds of loading and how good each of these were. So for instance, in granular jamming, it's terrible in tension. It works very well in compression in at least 2 directions. And it's terrible at shear. If you try to apply this kind of motion to it, jammed or unjammed, it's terrible at resisting those kinds of loading. Anyway, you can go through and work this out. And then this tells you when you might prescribe which type of jamming. And then we can distill this down into a smaller set of parameters that you often consider when you're designing this kind of mechanical structure. So things like conformability. Can I wrap this structure around another shape? Elasticity, order. So fiber in particular has this problem with order. You start out with everything nicely arranged, But if you unjam it and you bend it a number of times, those fibers are no longer like strings of spaghetti in the box before you cook it. They start to look like the spaghetti in the pot after you cook it. They all get tangled with each other. And so there are a number of these: bending, shear, tension, compression, and all these things you'd like to understand which to use. And so we map this out for each of these. So for instance, we can see that granular jamming is great for conformability, but it's absolutely terrible for tension. If you have a vacuum plastic bag full of grains and you try to pull it apart, the grains simply dissociate from each other. In compression, they're great. They interlock, they prevent compression, but they're terrible in tension. And in fact, this is true for all of the jamming media, that tension is the one thing they don't do very well. However, we've developed ways to use structural design to expand the media performance here. So for example, suppose we want to do tension and compression in our structure. Well, compression is pretty good for granular jamming, but unfortunately nothing is very good in tension. And so we can, however, take our laminar jamming, and by creating these flat structures, we can change this uniaxial tension and compression loading into bending on each part of the springs we designed here. And these springs, by the way, use a really nice fabrication technique. We start out by using a laser cutter to cut these intricate shapes for these springs. And then we put them inside one of our plastic bags, seal the edges, pull a vacuum, and put it back into the laser cutter. Now we can come along, and with the right power settings on the laser cutter, you can seal the edges of these intricate shapes and then come back through, turn the power up again, and now cut through the shape to remove the unneeded material. So with two fairly simple operations, you can use your laser cutter to produce these fairly elaborate laminar jamming structures. And so now this is a structure that's able to provide variable tension and compression stiffness, even though if you just pulled on the layers directly, they wouldn't work well at all. Another example, you might want conformability and elasticity. And the example here might be mold making. So suppose I have a shape. In this case, it's a squash, a butternut squash, just as a shape that has some fairly fine scale detail as well as large scale detail. So if I try to use the layers as a mold, I can wrap the layers around it, apply the vacuum, and get some jamming going. But when I pull this off and then I cast this as a mold, of course, it won't have captured any of the fine detail of the original here. Now, grains, on the other hand, can do a great job of conforming. They go into all these little grooves just fine. However, when I open up the mold, I pull apart my jamming structure in order to get out the original. Now it's deformed. It has taken a wider shape. And so the shape I wind up molding here, the green, doesn't look like the original very closely. But if I combine these in a single envelope, I have my laminar layers and my granular grains on top. I can now wrap this around the squash, apply the vacuum, and when I open this up in order to pull out my original, the layers provide elasticity. So I get spring back to the original shape, and they take the grains with them. So now I get much closer fidelity to the original shape and good fine detail at the end of the day. Okay, so that's the sort of fun research we've been doing with laminar jamming. Let me now just mention a few larger sort of things. The first I'll mention is that a lot of our tricks and how to do this fabrication, we've posted on the Soft Robotics Toolkit website. And if you haven't run into this before, it's quite a useful website about all things soft robotics. So my colleague at Harvard, Connor Walsh, started this a few years back and encourages people. It's curated, so people post designs, techniques, methods, results, which appear there. And we've contributed a lot of information on how to build these laminar jamming structures. And it's gotten literally millions of hits. Apparently now, if you go to a high school science fair, you will inevitably see a soft robotics project using the information provided on the soft robotics toolkit. We've also done a lot of STEM outreach. So as you might guess, this is an NSF funded project. And so outreach is, of course, one of the requirements, basically, of NSF grants these days. We've run workshops with lots of middle school and high school students. It's a very accessible technology. We've also built some demonstrations to help to understand concepts of impedance and stiffness. Here you can see this marker has been attached through a jamming element to a handle. And when it's stiff, of course, it's much easier to get precise tip control than when it's floppy. Busa Akas, one of the students working on this project, is also an artist. So she is also a sculptor and is the only PhD student I have had who is getting a minor in studio art as part of her PhD. And one of her exhibits was this tactile art using this jamming behavior. So you can get beads, this is like the beads that go in stuffed animals apparently, or beanbag chairs, put them in various shapes of sleeves and coils and such things. And users can come in and interact with them, make them stiff, form structures, all sorts of stuff. I did see a lightsaber fight when I visited the installation using these kinds of structures. And we originally had a half-day tutorial at ICRA 2020. And of course, the conference went virtual. And our tutorial was a hands-on session showing people how to build these. So unfortunately, that didn't happen. We are thinking of trying for this year's ICRA, although I think it's not quite clear yet how much will be in person. So we'll probably do it the following year, 2022. So long-range planning, stay tuned. All right, and I want to be sure to acknowledge the people who did the real work here. Yash Narang and Busa Atkas and Alprin Dermenji were the PhD students in my group who did most of the experimental work, a lot of the modeling. Nick Vasios is Katya Bertoldi's PhD student who did the finite element work, and Jost Vlasic is the applied mechanics guru who did the analytic modeling. So with that, thank you for your attention, and I would be pleased to take questions.
Woo. I could say I'm sure we're all applauding remotely. That was an amazing talk. I'm sure lots of people have questions. I can get the ball rolling on this. Actually, I had a question related to your wrist orthosis. So I know you I saw it go maybe deliberately out of frame, sort of the piece connected to whatever pneumatic compressor you have actually running the device. I'm curious, what, and actually I may have some ideas on this front because we've had Rob Matthew and Sarah Secco and a couple of other students in Rujna's group have worked on portable, using little compressed air type, CO2 cylinders that you might use to drive your bike. But I'm curious, what levels of air do you need? How do you see this evolving in the space of sort of portable jamming devices?
Yes, very good question. So yeah, carrying around a vacuum compressor isn't perhaps the most practical thing in the world. I will say we have found some pretty small compressors, battery powered, and the trick is an accumulator. So they're slow. So if you want to repeatedly cycle on and off, then you have what is effectively a small tank you pump down. And then when you cycle it, you'll draw that down, and then you have time to pump it back up again before you need it. But I didn't mention this, but there are a lot of other ways to actuate jamming. So one example is with springs and compressed air. So I can have springs that compress the layers, and now my airtight envelope can be inflated to force the springs apart. So now it's flexible. So compressors may be easier, compressors generally are smaller than vacuum pumps. But there's also electrostatic actuation. So Steve Collins at Stanford has a very cool laminar brake, which is based around applying voltages. So, you have a high voltage or a positive voltage on one side, a negative on the other, and a small layer of insulator, and now they want to stick to each other. The bad news about that is the voltages tend to be pretty high, at least several hundred volts at this point. And the problem is if you make your insulator thinner, so you can use lower voltages, you get shorting. And little tiny holes develop because of the sliding between the layers, which ruin the electrical insulation. So that's still an open problem. And, we can wave our hands and say, oh, that's just engineering. The principle is clear. But I think there's a lot of engineering to be done to make that one work.
Sure. Yeah. No, but that's very helpful. I think that's. I guess the answer is that it's going in a bunch of different directions then in terms of that technology. Yeah, I think I'm happy to moderate questions, but if we're a small enough group, if anyone wants to just chime in with a question.
I do see Hannah has her hand up, so we might start there.
Sure, Hannah, and then Ken will get yours from the chat as well.
Yeah, thank you so much for that talk. I mean, it's just such a clever and simple idea, which is just so enjoyable to see. And that's actually where my question is. Like, I can imagine how your students were in lab with printer paper and like, why don't we try this? We have it on hand. And you alluded to sort of redesigning those materials in terms of the sandwich design, where you have the outer layers that are different. How much have you guys explored different materials as compared to paper, or is it just like this golden material that happens to have the properties you need?
Yeah, so you have nailed it there. And it's weird and maybe even slightly embarrassing that paper is this magic material. It just works really well. It's the first thing we tried. And after trying dozens, maybe hundreds of different materials, it's still the best. So it has this great combination of good and repeatable surface friction and lightweight and low cost. And it's hard to find other materials that work that well. Friction is a messy thing. We all learned Coulomb's friction law in our intro physics class. And let me tell you, that is not a law. That is a crude approximation on a good day. And somehow the friction of paper, maybe because it was originally designed for writing, where you're sliding over it with a pen or a pencil. But anyway, the frictional properties of paper are shockingly good. So we've certainly used a lot of other things. Metal thin layers of spring steel also work quite well. Of course, there you've got to be looking at much higher forces. And you also have problems with plastic deformation. If you bend them too far, you get a permanent set. So you have to limit the range of motion there as well. So there's still a lot of work to do on the materials side of this, but thank God for printer paper.
Thank you. Yeah, it's so fascinating that maybe there is this like tactile feel. It was designed for consistency. And also just it is this product that everybody has an expected standard for. So that's such an interesting point. Thank you.
Yeah.
All right, great. So Ken, I guess, did you want to read your question or should I read it out?
No, go ahead, actually.
Sure. So I guess reading from the chat, Ken is curious how the materials perform over time in terms of do they wear and change their performance or characteristics, or are they pretty robust?
Yeah. So first, I better say we've never done real lifetime testing, performance testing, but we've certainly done thousands of cycles with some of these. Paper is, again, shockingly good. The big thing that changes the frictional behavior can change of these other materials. So we've used plastics, and if you slide plastics against each other, they can produce some small bits of dust, apparently. And we haven't done a great analysis of this, but you will find that the friction changes. And interestingly enough, it'll go in different directions. On some plastics, it'll get higher, and in some plastics, it'll get lower. So again, the material science of this is a long way to go. But the other thing is the plastic bags leak. And so, the plastic has actually been more of a long-term problem than the sheets of material inside. And my students have gotten very good at finding leaks in thin plastic bags.
Okay. So I'm actually curious, just to follow up really quickly, is that, I mean, I think that could be solved maybe with better materials, but I'm curious that the controls may have to be adaptive in some sense, right? Because over time, the response characteristics are going to change. So they have to, in other words, the same controller will start to not work as well.
Oh, that's interesting. Yes, you are completely correct if you were trying to actively control properties. But I will say that points out to me for the first time that I've thought of this in a very different context. So I've thought of this as a passive behavior. The idea behind a lot of our work on robot hands, for instance, under actuated hands, is to say, I want to get the passive mechanical behavior very close to the overall performance I want. And then I'll close a controller on top of it. So if I have compliant fingers that like to adapt themselves to the object shape, I don't have to actively control every joint to get exactly the right grasp. And it's the same kind of thinking here. The way I have thought of it in the past is, oh, I want it to be floppy, turn off the vacuum. Oh, now I want it to be stiff, or I want it to be a damper, turn up the vacuum. Linear control, which you could get, for instance, by changing the vacuum level. That would control the yield point when you turn the damper on, or how much energy you dissipate with the damping. There, you're right, you'd have to have some kind of adaptation. But if it's just this switch between floppy and stiff, or floppy and dissipative, maybe not. Maybe you can tolerate a big range of plant changes.
Great. Okay, thanks, Rob.
Any other questions? I guess your hand is still up, but I'm assuming that was your old question.
Yeah, for some reason I can't put my hand down.
Oh, here, I think I can put it down for you. There you go. Yeah, I mean, I have several more if no one else wants to chime in. I guess I'm curious.
For Hannah here. Hi, this is Michael Vanner down in Santa Cruz. We're fortunate enough, we have a guy who did a layer jamming project for his master's degree before he joined us. And he published a bunch of different materials he explored. So we can send that your way if you'd like to see it.
Oh, it'd be very interesting. Yeah, great. Or stick it in the chat and we can harvest it.
All right, thanks.
Might end up on the repository online that everyone seems to be using.
More publicity. Who doesn't want that for their papers?
Cool. No, and I think I don't know. I admire that a lot as well. I try to put all of my data sets up online, and I think that's a great. I guess sounds like not just a contribution to the scientific community, but also the wider, I guess, educational community too. I think that's awesome. Yeah, I think I had a couple more questions. One, I guess, related sort of to my earlier question about the orthosis, but actually this last conversation about control is, I'm curious if you thought then about sort of the UI side of this active versus passive control, and how an eventual user of an orthosis would interact with that sort of active passive system, and what you think the user would experience then, what that control looks like.
Wow, you're way ahead of us. I think a simple switch, people will know either they need a brace or they want to get rid of the darn thing. And I don't know if it would need to switch dynamically. So would it need to switch in the middle of a task, or would it be sufficient to use a switch to change it? I will say that learning to rely on it actually takes a little while. So with our subjects, we had to kind of teach them to let the brace carry some of the weight, that they were inclined to just push against the brace, because that's the normal behavior. That's, I have to hold up this weight, I'm going to push. And no, relax, it's okay. You don't need to do that. So clearly some training will be required for people to actually make use of this thing effectively.
I guess if you are interested in moving in that direction, there's some work from the Baichi group, specifically Robert Matthew and some of their old undergrads as well, working on an active passive exoskeleton for, I think they were targeting individuals with muscular dystrophy, but a similar sort of intermittent control to different levels of stiffness. So I'm happy to pass on that literature too. I think it's really relevant here. Yeah, I guess my second question was much more broad. I know you work also on surgical robotics. I was curious if you've thought about this intersection between some of this jamming actuation and the surgical applications.
Yeah, so as I mentioned, there's a group I cited who's done a surgical manipulator that has this jamming. And this is actually something we've run into in our beating heart surgery. So we have built catheter robots, which can be threaded through the blood vessels into the heart and can do things like place anchors or burn tissue, cut tissue, and so on. But one of the problems we have is that you want this thing to be floppy as it's threading through the blood vessels. But when you get to the other end, you got to apply, a 2 Newton force. And it's hard to apply a 2 Newton force with a floppy noodle. And so jamming is part of the answer. But when you're emerging from a blood vessel into the heart, just because it's stiff doesn't mean it won't still flop around. So we need some combination of the stiffening of the actuator of the catheter, and also some way of bracing, some way of extending out to nearby parts of the heart to get a firm grip, so you can now insert your anchors or whatever you need to do at the distal end.
Wow, super interesting. I'm excited to see where that work goes. I know we're now over time, so if are there any last questions before we wrap up? We can definitely stick around a bit. Okay, so I think we'll officially close now. I can be on the line for a few minutes to facilitate if there are any last questions, but thanks everyone. I think Andrea, we can stop the recording and